Alright, hi Silarians, I'm here with question 5. Alright, this the velocity time graph of a ship. Right, when we look at a velocity time graph, we always think about two things. The gradient of a velocity time graph gives us acceleration, and the area under graph gives us displacement. Alright, so the first part of the question asks us to calculate the total distance traveled by the ship. Alright, and part 2 is the total displacement of the ship. Alright, so I'll do these two parts together. Alright, by trying to figure out the area under graph of this VT graph. Okay, so what I'm going to do is I'm actually going to break this graph into 5 parts to make my life easier. Alright, I'm going to break up into this part, right, and call it A. Alright, then I'll break up into this part and I'll call it B. Right, then this is C, this is D. Right, then I dotted here, and this very small part here I call it E. Alright, this part is not marked, but if you read the question you realize that it's 320. Okay, as per this number over here. Right, I know that area under graph is my displacement, so I straight away try to figure out what the area under graph here is for A. Right, for A is a triangle, so it's half times 5 times 50, which will give me 125. Alright, so the area under graph for A is 125. Right, area under graph for B is this length over here, which is 100. Right, 150 minus 50, so this length is 100 multiplied by 5, which is 500. Okay, this area over here is a triangle again, so it's half times 5 times 100. Right, so half times 5 times 100 gives me 250. Alright, so far everything, the answer of the area has been positive. Alright, because it's half times a positive 5 and a positive 50. Right, here is a positive 100 multiplied by positive 5, and so on and so forth. Everything is positive, so not surprising, my area under graph for A, B and C is positive. But when I hit D, my area under graph actually becomes negative. Why? Because it becomes half times, alright, this length over here, which is 50 multiplied by this length over here, which actually is minus 2.5. Alright, so this is the first time the area under graph becomes negative, which actually implies to me that my displacement suddenly moves in the suddenly the displacement for this duration is actually in the opposite direction to this direction, this direction, and this direction. Okay, so I'll explain to you what that means in a moment. Right, for E, again I calculate. I assume you know how to half times base times height. I'm just going to give you the answer as minus 25. Right, then I'm going to plot this in a manner that I can understand physically. I want to know what the ship actually physically does. Right, so firstly I will know that if let's say the ship moves right, okay, you can take it that the ship moves up. Alright, it doesn't matter, just that you get a vertical line instead of a horizontal line, but the meaning is the same. So I'm just going to choose right as the direction of the ship. So the first time the ship starts from here, it moves 125 meters to the right, then he moves 500 meters to the right. Alright, so I know this 500, okay, this 125. Alright, then I will move some more, 250. Right, so I should try and make this arrow bigger than this one. Actually, it should be double the size. Okay, but if I put numbers, then I'm not so worried about the arrows being not exactly drawn to scale. Alright, my diagram is obviously not drawn to scale. Okay, so I keep moving towards the right, 125, 500, 250. Now I'm here. I'm actually very far away from my reference position, and that's at this point I'm actually here. Can you see that? Right, because I already traveled A, B and C distance away from reference position. Then suddenly my area under graph from 250 to 300 is negative, and it's negative 62.5. So it's actually a very small distance back. Right, I'm moving like that. Right, because this is a negative. Right, so remember what we said earlier. We said that the reference is always taken to be the initial direction of motion. Okay, it's not always but 99% of the time Okay, if the reference is right, because I start moving right earlier, then once I get negative displacement, it means that in this time instant the change in displacement is actually negative. So I'm moving in this direction instead of the right direction. Right, this direction is left. Right, you either move right or you move left. Alright, I stress again that in your syllabus, when you look at the graph, it's one-dimensional motion. Alright, so if you assume the ship's initial speed is to the right, the only thing you can do other than move to the right is stop or move to the left. It cannot do up, it cannot do down, it cannot do northeast or southwest. Not possible. Alright, so you can see that here is moving right because the area is positive. Here I'm moving right because area is positive. Here I'm moving right because the area is positive. Here I stop. Why? Because the velocity is 0. Right, that's why I stop. Right, then D, I'm moving left because the area is negative. Right, so that's why you see D, I'm actually drawing something here. Right, and this thing should correspond to 62.5. Okay, I'm really sorry about handwriting. Okay, I actually forgot to bring my stylus home. That's why it's quite difficult to draw with the mouse. Okay, again, here the last part is negative 25. So again, this is 25. Alright. So if I were to ask you, what's the displacement at t equal 50? Alright, because I'm here, my displacement is actually 125. What's the displacement at t equal 500? What's the displacement at t equals 150? Right, where I'm here, right? So the displacement is actually 125 plus 500. What's the displacement at this point? Right, is these three figures add up together, right? So that's the displacement until here. What's the displacement at this time, which is t equal 300, right? Then I have to figure out that actually at the time t equal 300, I'm here. Can you see that? So my actual displacement is from here to here. Alright, and then finally, what's the displacement at time t equals 320, which is here? Alright, then I will be here because I move back by 25. Right, so now be careful because the question asks you what is the displacement of the ship at t equals 320. Right, remember at 320 I'm here, right, because I moved negative 25. Okay, this one is negative and negative. I moved negative 25 back already. Now the displacement you must remember is always from reference position to the position I'm currently at. So that is actually this length over here. Can you see that? Alright, it's from here to here. That's why I said that actually area under graph very specifically is the change in displacement. It's not the actual displacement at the point of time. If I'm looking at this area under graph right, it's actually the change in displacement from this point to this point, which is negative That means I'm moving back. But if I ask you what is the displacement of the ship here at 320, actually the displacement of the ship is positive, because it's from displacement is defined from reference to the point. And if you draw a line from the reference to the point, the direction of the arrow is to the right, and the right is taken to be positive, right? So that's why when you do a calculation for displacement, you actually sum these three areas, then you minus 25 and minus 62.5. So you should get something like this. Actually this 787.5, right? So this length over here, I'll try and draw it nicely for you. This length over here, right, is your displacement. This is the start. This is after E, right? So and this length is to the right, right? So actually this length actually is represented by 787 meters, right? If I want distance, right? Distance don't care about direction, right? And don't care about reference position. It's just how much you move. Right, so if how much you move is just 125 plus 500 plus 250 plus 62.5, I don't care about the sign, because if I move here and I move here, it's also distance so I plus 62.5 and plus 25. So you see, when I want distance is sum everything, right? You sum this number, this number, this number, this number, and this number. Don't use the negative sign. When you find total distance, you should get 923. Alright, so that's the difference between displacement and distance. Alright, stay tuned for the next part. Actually I'll do this average velocity first. Average velocity is just change in displacement over change in time. Right, so it's easy. I just take the change in displacement, I park here, then I know the time taken is 320. So this average velocity is an easy part to cover. Right, I think deceleration here is also easy so I'm going to just cover in this video. Sorry, I'm going to extend it a bit longer. Alright, so I use deceleration at time t equals 200. Okay, I think it's very ugly already. Let me see, never mind. Okay, so deceleration at time equal to 200 is this, right? If I want deceleration, actually, there's no formula for deceleration, right? So what I do is I calculate my acceleration. Okay, then if there's a sign in front of my acceleration, I throw away the sign. Okay, so acceleration, how to calculate? I think this one you all don't find it difficult. If I want the acceleration, is the gradient of the graph, right? I mentioned in the earlier part of the question. How to find the gradient of the graph of this point? The gradient throughout this motion here is the same, right? This whole line have the same gradient. Right, so you just take 2 points here and here, right, and find the gradient. Alright, I'll explain this after I clear the the diagram. I know it's a bit messy. Okay, see you in the next part of the video. Okay, there'll be a part 2 for this video.